Good. Okay, right. Hi, everyone. Sorry for the late start. So I did promise that today we talk about RL. I think the title slide is a little misleading. Because I'd started making this presentation with general foundations in mind, and then I remember that we kind of talked about we started talking about like GRPO versus the approaches that I've been using in my work. And we got a lot of questions about like, what are the differences? What are the similarities? How do you, extend one to the other? And so what I'm hoping to do through today's slides is like, I'll present a little bit more about how DGPPO works. And then people who are working actively with GRPO or have more context than whatever I present on the slides. I'd like to hear from the group on that. And then at the end, there's like a little bit of space for some discussion questions, thinking about how we could integrate those architectures and where would it be useful to maybe have hard constraints for GRPO type problems or have that scalability that GRPO has with what are typically critic-based problems. Okay. Let me stand on this side. So we briefly talked about MDPs, which stand for Markov decision processes last time. But an MDP is basically a model that helps with the decision making for a robot. But the outcomes are like half random, and not actually half, but like partly random and partly under the control of the agent. So the way we represent an MDP is with this representation, S, A, P, R, and gamma, and this is the breakdown of what each of these mean. So the S is the state. So when we work with any sort of state space model, it's just what is the current configuration of the environment. And depending on what kind of problems you're dealing with, your state will adapt accordingly. So your state could include the current position, could include the current velocity. It could include like battery status, like any information that is relevant to know about the robot or about the agent at a given time is something that can be stored in a state. And then our action set. So all of these are the sets, not just a single action or state. So the capital version is the entire set, possible state of values, possible set of actions. And then if you see it in lowercase, so like this, that's a specific state or a specific action that you could take. So the set of actions would be like, if you're doing discrete motion in a grid, it could be forward or backward or left or right, or like stay in the same place, right? So action spaces can be discrete or continuous, depending on, again, the problem at hand. And then you have the types of transitions you can make. So if you've seen those like state machines where you have the different states and then you have like an arrow that goes from state 1 to state 2. What determines what takes you from state 1 to state 2 is the action. And each of those like connections between pairs of states are their transitions. And sometimes you can assign, so this is not like relevant to this part, but you can assign probabilities to these transitions. You can have from a given state, from state A to state B, with some probability you could get to state B, with some probability you could get to state C potentially, right? Like there could be different reasons that you do certain things. So this transition kind of set is, in our case, like the kind of motor commands we could do. And then we have our reward, which we talked about extensively in RL, but that's basically a scalar value. It's the feedback that you get based on an action you take. And it can either be, so typically it'll, typically we want to maximize reward and we want to minimize penalties. And penalties can either be baked into the reward or they can be treated separately. So like in DGPPO, we have a certain type of penalty, which is separate. And then we also have penalties that were baked into the reward, if you remember from last time. So we penalized going into the wrong region, but that's like a soft kind of penalty, which is why it's included in the reward. And then we have our discount. So the discount is basically just a multiplicative factor, which like diminishes information from the past, but retains it. It keeps some of it, right? So I don't care. I care a lot more about what just happened than what happened 100 steps ago. So I'm discounting that 100th step ago a lot more than I am the step that I just completed. So that's basically what this discount factor does. Yeah, so that's the general basis of what the MDP structure is. Again, we represent it in the MDP because it's a really nice way of like abstracting away the problem, representing the environment and the problem that we're thinking about. And so this is just a.
I'm sorry, S prime is just future state, right?
S prime is a future state. Yeah, exactly. So this is like, what is the probability of getting this future state S prime given your current state and
So here
action?
it says that what is the value and maximum over the possible actions? It says maximum the value of current action, the reward of current action.
This one?
The left one. A little bit left to the RSA.
Oh, here, yeah.
Is the reward that I will get when I do the current action that I'm looking into.
Yeah.
And then what would be the future?
Correct. So sorry, did I say past? I meant future. So this is saying like you could take an action. So you could take an action right now, but that action may result in a bad path going forward, right? So if you're greedy and you only look at the best next step, you could be like, it could mess you up in future iterations. Or like you take one step and it's great, it maximizes your reward right now, but that could just lead you like downhill as opposed to going up. So that's why we care about thinking about the future. So this is like it's like a forward prediction of your value. Okay, so this is just a visual representation of all of this basically. So you have your agent, which is interacting with the environment, and it interacts with the environment by executing some action. And by executing the action and interacting with the environment, you get updates to your state, right? And then you also get information about basically what is your new state now that you've executed this action, and what is the reward you get for executing that state. So that's what that's meant to represent. And when we think about like what reinforcement learning is in the context of MDPs, it's just the process of like how this agent is interacting with the environment to then solve the MDP. So MDP again is our world representation, and an RL, the output of reinforcement learning is a policy, which tells the agent when you're in a certain situation, if you act a certain way, this is the kind of output you would get. And by chaining these actions together, you can get like an optimal output, or navigate through the environment, do whatever you need to. Yeah.
Is there any maximum depth of the recursion we see here? So
For this part?
yes, for example, how in the state S, and we want to estimate also the value of the next environment state.
Yeah.
And this goes recursively. So is there any number of steps we want to look forward normally?
I don't think no. So this VS prime is another like expected value of that state. So it's not really like, it's not recursive to some depth. Yeah. Any questions about this problem setup and like the basic math of the MDP? Like I did not put too much math in the slides. This is the most like heavy representation that you need to know, kind of leading into. So like most RL papers are going to use this kind of these symbols and these definitions. So knowing this is pretty important when you start reading papers in the field. Okay. All right, so I will move on. So we've talked very briefly about imitation learning versus reinforcement learning. I don't know how many people are like familiar with imitation learning itself, so which is why we'll talk a little bit about it. But the idea with imitation learning is it's exactly as it sounds, like imitation. So you imitate what you've seen where you've seen like correct examples. And so it's almost like a copy paste type of scenario. So you give it something, you tell it that this is how you do the task correctly, and then it learns how to replicate it or mimic it with its own dynamics and whatever it needs to learn. Right. So that's like if I was saying, like, this is how you fill a cup of water. And the only examples I've given are like an upright cup, an upright mug, and then the actual pitcher, and then you pour the water in, right? So it can copy that, and it can learn how to do that well. But then the challenge comes in where, like, what happens if you're suddenly given a scenario where, like, the cup is tilted, or the pitcher is further away, or, you know, scenarios that you haven't really encountered in training. An imitation learning problem won't know how to handle something like that, right? Like it'll try to do the thing that it had learned just by copying it exactly. So it's like the kids who take a test and they just like memorize like the answer key, and they try to go and apply it. It's the difference between learning the concept and just learning like what was on your homework, let's say. And so RL would be the smarter student, which learns exactly how this thing works, right? Like, what are the mechanics? What is it that I actually care about? Like, I care about maybe my grasping of the mug. I care about my grasping of the pitcher. And then, like, those are a lot more complicated things to think about. So because RL now has this ability to maybe learn from its mistakes or learn from other like variations in the environment, so it does this by exploring your state space, but there's both good and bad things that can happen, right? Like you can find recovery strategies or like shortcuts that are good, right? Like good for execution. But you can also get things which are the reward hacking we talked about, which would be bad, right? So it'll find a loophole maybe. So there's a difference between a shortcut and a loophole, right? Shortcuts might be good, loopholes are not typically. So this was also the motivation for the whole splitting our safety problem into its own component and not including it in the reward. Because there could be a scenario where driving straight through the wall gives it less of a penalty than, you know, going all the way around and doing what is safe. So this is a really important thing that people who work in RL like struggle with sometimes, right? Like, how do you know how to balance your reward function so that you don't get this kind of reward hacking, but you're still motivating your robot to do the right thing at each step or guided in that direction. And so this is just terms that keep showing up. We talk about like actor-critic setups. So PPO is an example of that. And DGPPO, again, adapts the PPO algorithm. But the actor is the part which learns how to move, picks the action. The critic is the part which tells you it's like the checker, right? It tells you how valuable is this action for you? How much is it, you know, better? Is it worse? Like, is this a good choice? Right. So it's your like conscience when you're taking whatever action. And when we talk about PPO in the context of other types of RL algorithms models, the important thing about PPO is we use this clip loss so that you're not moving too much along a policy gradient. So it keeps training a lot more stable. And again, this is all relevant because when we do exploratory tasks, you have to be really careful that you don't fall into some like local minima or something else where you can't get out after some amount of exploration. So you want to, there's like this trade-off of like, how much do we want to explore? How much risk do we want to take about this decision? So that's where this clip loss comes into play. Any questions on this slide, IL versus RL?
You know, I want to add one idea that from the learning, like it's, I don't know, LLM perspective, the imitation learning, when you give the correct path, that's kind of a denser signal regularly when you get through regular RL. So usually with RL, your reward is not very like dense at
Consistent,
each
yeah.
step, right?
Yeah.
Although in some cases it can be.
Right.
But usually, like, I don't know, there's regular examples of, I don't know, chess, right? You play and in the end, you know when you win or lose. So your reward is kind of sparse.
Mm-hmm.
In case of imitation learning, you have all the steps.
Correct.
So you have very dense signal, although it might not cover the whole whatever space, right? So I think that's, at least in my head, is the trade-off between these two.
Yeah.
Like how dense you teach.
Right.
the
It's like
models.
all closer to full knowledge, basically, with imitation
Yeah.
learning. And then
Yes.
reinforcement learning is like, I've given you some information and some of it you have to figure out yourself, but I've given you tools to tell you, like, are you doing the right thing or not?
Yeah.
Like, I think the way I always explain RL to people who don't have a background in computer science or who are new to the whole space is like, think about how a child learns, right? You don't handhold a child for like them standing up and walking, right? Like they make mistakes, they fall down, they get hurt, they cry, and that's that's in their reward function. And then so that's like a penalty, right? And then when they successfully make a step, parents like clap or they smile or like there's a sense of joy, and that's a positive reward for them. So they know that this thing is right and that thing is wrong. It's the same thing as like touching a hot stove, right? That's hot.
Yeah, one question. So, I mean, when you start from scratch and try to train a RL model, sometimes, you start from a very random state. So
Yeah.
it takes like
Forever.
infinitely long usually to go somewhere meaningful. So is it actually, do they in practice do the following to like to seed kind of to somewhat correct the solution by training a bunch of IL cases, and then after you train something,
Yes.
seed it somewhere and then training the school or
Yeah, so that would be like warm starting or pre-training. I believe so. Like you, like that's a very reasonable way to approach the problem. I think like now enough things have been, put out there that it's easy to take something, use that as your warm start to pre-train. But I think starting anything from scratch it's like true of any type of machine learning model, right? Like any neural net you train from pre-training versus training like pre-training, warm starting with pre-trained weights versus just randomized is going to have significant time differences. And I guess it also depends on the type of task you're trying to achieve. Like maybe reaching an XY position, you could start without much pre-training, like you could probably start with pretty randomized weights, but something more niche or something where it's not as simple of a task, I think we need more of that domain knowledge, which would come from maybe an IL kind of problem. Yeah, great question. Any other questions, comments? People who work in this space have other comments they'd like to have? Yeah.
I think I would add to that one that ChatGPT is the best example. So in that sense, when you're talking in the LLM terms, this imitation learning is the SFT, which is supervised fine tuning, when you give questions and exact answers. And then there is this GRPO or PPO or whatever RL, where you give questions, you don't give the correct answers, but you rank the answer candidates given by the model. That's how the reward is being shaped.
Correct.
And all modern ChatGPT style models, including Gemini, go through these steps, which is equivalent to say that they go through imitation learning and then go to RL.
Yeah. That's a good point. But yeah, I think like the key difference is the information that you're giving at the start. And like that's the biggest differentiator. And that obviously influences the structure of the models and how you train it and things like that. Okay. So let's see. Yeah. So in these like PPO models, and both for DGPPO and GRPO, we think about that like exactly what Harant was saying. We think about like value in a maybe slightly different way, right? So they call it an advantage function, capital A. And what we care about is like how much better is this action compared to your average behavior of your current models, right? Like, is this a better action to take? Is it a worse action to take? Is it just like normal? And anything above average is a fine action to take in some sense, right? Like, you don't want to take something that is below average at the very least. So you can use that as some sort of a guiding factor. It doesn't need to be the optimal. It doesn't need to be the best, right? It just needs to be better than most things in your current set of examples. So when we think about why, like, framing it this way is relevant, as in like why GRPO and DGPPO are so different, is this bullet, right? So with an LLM, a bad output is just a low score, a bad response. It's like you ask it to do 2 + 2 and it says it's 3 or something, you know, like whatever, it made a mistake. But if you get 2 + 2 = 3 in real robotics, then you know, that's like the drone crashing or whatever it might be, like pursuing the wrong target, something like that. And so when you care about different things in different domains, that affects, again, like what you prioritize in your models, what you prioritize as being learned. So for GRPO, we talked about like the critic and how the critic doesn't exist in GRPO. So I'll talk about that in a later slide. But the reason we can do that is because in GRPO, we ask the question, am I doing better than the average in my group? Literally by like sampling a group of peers. So you can produce multiple samples for a given prompt, let's say, and then see where your current output lies within that distribution, right? Is it a better response than most of the things that you see? Great, then accept it. If it's worse, then try again, right? And so training a critic can be pretty costly, pretty expensive. So by removing that, you're saving a lot on memory in a GRPO type structure. And because it's very easy to like spawn results, like you can maybe get 64 responses to a single prompt and then compare across them. That's a much faster operation with with an LLM. But something like that doesn't necessarily apply to robotics. I think like simulating that many trajectories can be a lot more expensive than having this critic come in and handle it itself. So that was GRPO. DGPPO, the priority is you want to reach some target, but you have to do it safely, right? And we define some unsafe set with our CBF, or control barrier function. And what we're learning is not just how to move, but we're also learning like what defines the boundaries of our safe set. And you use a critic in this case. The critic would be some neural net kind of structure. This question we kind of answered on the previous page, but we don't want to just have a negative reward for safety, like collision avoidance or crashing, because if you have a imbalanced reward function, then reward hacking can cause you to just ignore the safety component. And I think someone asked me at some point, like what the the discrete part of DGPPO is meant to be. And that's just to emphasize that we're dealing with discrete time, because when we're thinking about hardware and real robots, things are happening at a certain frequency. They're not continuous. And so you want to like model the fact that if your controller is working at 100 Hertz, let's say, you are ensuring safety at like you recalculate your policy correctly according to whatever frequency your robot is operating at. So we're not treating it as continuous, we're treating it as discrete time space. So that's where the D part comes from. We've briefly talked about the G, the graph. I'll talk a little bit more about that. And then the PPO is obviously using PPO as your base algorithm. Yeah. Any questions on this page?
How exactly do you ensures that safety is checked?
So the PPO part of it is not, right? So the DGPPO is a two component kind of thing. There's learning how to execute execute the task. So figuring out what actions you should take. And there's a GCBF, so a graph control barrier function, which is also learned simultaneously. And that's what is ensuring the safety. So a CBF gives you mathematical guarantees on your safety, because you're basically applying a hard constraint where you say if you cross this certain threshold, you're in an unsafe region. So by learning where that boundary falls based on your relationship to your neighbors, you can ensure that if you're going to take an action that would take you over that boundary, you basically ignore the reward that you would get from that action, and then you take a corrective action to get back into your. Yeah, so I'll, I think I have a slide, one or two slides, which should go through that, but yeah. I think I kind of talked about these, but, GRPO is able to remove the critic because you can efficiently sample multiple outputs for the same prompt and compare them. So we don't actually care how good is this, we just care how good it is compared to your peers. But again, with, robotics, since we care about the safety, we keep it so that we ensure we maintain this hard constraint and not a relative ranking. It's not saying like, you know, crashing into the wall for 1 second is better than crashing into the wall for 5 seconds. Like, yeah, that's true, but you still crashed. Like you do care that I would rather not crash at all. So, the binary is more important in this case than a more continuous kind of space of options here. Sample efficiency, again, we talked about this. And also, this last part is pretty important because we have this graph, which is looking at, so we build the graph part of DGPPO only looking at a certain sensing radius. So for me, maybe I only care about, and like I care about all of you in the room, but I'm saying maybe I only care about collision avoidance with the first row when I'm navigating. Like, so people in the back corner are not going to affect my decisions right now, right? So it doesn't make sense to include that in my sensing radius. So in some ways, it's like a decentralized graph where each agent in the graph sees a different view, right? Your view depends on your sensing radius. And so you need this critic to act as like some type of internal judge, which can, you know, ensure that the right option is being chosen at each of the nodes or for each of the agents, as opposed to having them try to communicate with each other. That would just increase the complexity pretty significantly. Yeah. Okay. So it's probably useful to better understand the DGPPO structure. And what we have is 3-ish kind of layers at like a high level. The first is where each agent, so this is what I was just talking about, but each agent has some local observation based on your sensing radius. And there's like an MLP encoder which takes whatever is in the state. So in DGPPO, they keep position, velocity, and whatever sensor readings. So in the original, they don't have sensor readings. In our version, we have our current cluster. So that would be considered a sensor reading. And you keep track of LiDAR scans of obstacles or people you were close to. So all of that gets encoded. And all of this information you have is like collected and shared along the edges of the graph, which is why we use and impose this graph structure. The middle part is this message passing, which is basically edges are created between agent I and any neighbor J within its sensing radius. And then information about that relationship is stored. So distances or any other relevant information that you could want to add. In the second step, the base structure of this model is a GNN, a graph neural network. And what the GNN does is it aggregates all the features from all its neighbors. And it uses functions like summing or taking the average for the purpose of being permutation invariant. So what that means is like for a sum and for a average, it doesn't matter if 1 comes before, if like 3 comes before 1, right? Like it just matters that you have a sense of what is around you, and you don't really care about the relative order of their position.
No attention.
Huh?
No attention.
No attention, like as a layer.
Yeah, it's just song and the attention to different layers, different.
It doesn't, so in this case, it doesn't really care about different neighbors differently, except for like information that is in, so information that would be encoded by this would be relative distances, right? So like I'm closer to her aunt than I am to you right now. So in some ways, maybe I'm paying more attention to him than I am to you as I navigate, but you're still a relevant part of, but it doesn't matter that, it doesn't matter if I like operate on you before I operate on him, like in my node structure. That's all that this is meant to say. So like it's none of the operations are like none of the operations are dependent on any order, if that makes sense. So which is why it's treated as a set rather than a list. So there's no ordered list of nodes. It's just this is the set of nodes that are in my. So it doesn't matter if I'm like looking here and I like start my set this way, or if I'm looking here and I start my set.
Technically, attention is also the permutation of query.
Yeah, so yeah.
GNNs do not have potential.
Yeah, I don't think it's.
It's-
Yeah. Yeah. In this case, I think like the information that is relevant between pairs of agents is the information that's stored along edges and therefore encoded. So that's how we handle that part of the problem. But yeah, so then when you think of graphs, we think about like information flow, we think about connectivity, and that's like exactly what that's like very useful in the swarm context or multi-agent context. So this was initially developed for the purpose of multi-agent work. And then I just took it and adapted it for what I wanted. So hopefully this makes sense of the justification of why we're using this graph structure and these two layers. And then once the GNN has done whatever processing it needs to do, it splits into the actor like path and the critic path. So the actor, since it's trying to figure out like what motions to do, it's a distribution over the various actions for a given state. And that's our policy high. And then we have the critic head, which influences our like feedback, right? So based on an action that's taken using the current policy, you take a look and you see, does this action make sense for whatever our purpose is? And then that will go and update the loss and then influence the rest of the model and pipeline. I'm just going to skip ahead real quick, but so what I'm saying is we have our split of the two paths. You have your policy actions, you have your safety part, and that meets together over here. So that's useful for this part, I think. So just to, I guess, on one slide, summarize why we care about the graph structure and why we use a GNN, especially in multi-agent systems, multi-agent environments, an MLP will just have a certain vector size, which you can fill with information, right? So that makes it a pretty rigid observer. But with the GNN, because we have this like message passing kind of concept, you can apply, you're just applying that operation on every single edge. So it doesn't matter if you have like 3 edges or you have 10 edges for a given agent. And that's really useful for modeling because as I move around in this room, I'm going to have various numbers of neighbors, right? So right now, maybe I have 3 neighbors. And then if I move into the middle of the room, maybe I have 10 neighbors. And if you use just a standard MLP, then like, how do you know what size of vector you should be using? Like your model would have to be retrained every time you want to expand to a newer set of, to a larger number of agents, let's say. And so that's a really nice feature because that means you can train for a smaller number of agents and then expand it to a larger set of agents without changing the policy. And again, this works mainly because what it's learning is the relationships between agents, not necessarily the topology of the agents or like, like I care about, for the purpose of like collision avoidance, for example, I care about just maintaining a certain distance from everyone, like say a 1 meter distance from everyone. Or for obstacles, I care about staying 2 meters away, whatever it might be. It doesn't matter that now I have, like obviously as I have more neighbors, that becomes maybe a harder problem to solve, right? Like I can't stay 1 meter away from every single person. Maybe that means that that's not a place that I should be, right? So that's like what we would learn. Okay, that's good. Okay, so but this is just a representation of GRPO's version of the advantage function, which we talked about. And GRPO just removes because we're removing the critic, we remove the value model, and instead we're just calculating the advantage with like normal statistics. So your current reward minus the average reward over the standard deviation of that distribution will tell you like how you're performing with respect to the rest of your current distribution. And the nice thing about this sort of baseline is that that'll like the mean is going to center your rewards. So anything positive is going to be better than average, and anything negative is going to be worse than average. So you won't be making negative decisions. And then in DGPPO, so this is GRPO, this is DGPPO. There are 3 things that are being learned. So we have the actor, which is learning how to move, what actions you take, which is the policy. And then we have the task critic and the safety critic. So they're notated as VL and VH. The task critic is doing the task of verifying how good the action is. And the safety critic, which is the GCBF, which is what we're learning, is asking, is this safe? And these 2 are used very different, right? Like this one is the hard constraint, and this one is like I wouldn't call it a soft constraint, but it has softer influence on the advantage that we just. This is a like visualization of their pipeline, the DGPPO pipeline from the original paper. Let me see if I have a bigger version. Okay, yeah, so I'll get to that later, but keep this in mind and we'll come back to this. Yeah.
Represented as a graph in all this setup. So
what is represented in the graph? So the nodes would be like agents in the environment. So like if you have 3 robots running around, you would have a node for each of them. Then you'd have nodes for like static obstacles potentially, and then you'd have edges that connect these agents to each other. And like, yeah.
And the graph is the state, the graph value is the state of the environment, including all the agents and the obstacles.
So the graph for a given agent will depend on its sensing radius, right? So the graph for me is going to be different than the graph from you. And I'm operating on my graph and you're operating on your graph. So there's no like global, you could construct a global graph, right? But for the purpose of operation, that whole like decentralized concept that was brought up before is because your sensing radius is like the things that fall within your net that you care about are different than what I care about. And you don't want to be like each agent should not be making decisions like thinking about what every other agent is doing, right? Like,
but as 2 different agents in the same environment, do we have 2 different graphs or are we 2 different nodes in the same graph?
Okay, so it's technically both, right? Like you might show up as a node in my graph, but your view of the global, so you can think of it like a global graph, and then each agent has its own view of what that global graph is. So you may show up in my graph as a node, but you may not show up as a node in my graph, sorry. But yeah, it depends. Yeah.
It's a point of clarification.
Yeah.
If it's my graph, I'm always the mean node. Right. Like
Yes.
It's like
yes, it's with respect to you. So it would be like you are the root in some sense, or you are the whatever. You're like the central node.
It's in code like a position, the origin or something.
I think like each node is assigned some like numerical node. So like you'd be like the 0 node, basically. Yeah. So everyone knows who they are. And the question is, who are you connected to? Or like, what obstacles are you going to encounter? What like people are you going to encounter? And obstacles you encounter is encoded by the 8 nearest LiDAR points that you see. So like if you had 36 LiDAR points, let's say, I only care about the 8 closest points, and that would encode some type of obstacle or something that I need to pay attention to.
So the graph from my point of view is something like the connected subgraph of the global graph
Exactly.
when I am included.
Yes.
What is the node and edge features?
Huh?
Node features on the edge features in the graph.
Node features and edge features. I can pull up maybe the code base will be a useful visualization of that actually. So the things that we generally care about are like state features, so position, velocity, things like that. And then for collision avoidance with obstacles, like that's the position of your LiDAR hit point, and other agents that exist in the graph that are within your radius. So those are like those are where edges, like those are the those will determine whether you draw an edge between you and something else in the environment.
For the same.
Sorry, say that.
The same inputs.
The
So yeah, you said it's only in the last layer that they,
yeah, so where they split is here.
which means the inputs originally on the left were the same. No?
Yeah, so all the inputs are the same, and where it splits is just at the critic stage of the top part is the normal critic that we deal with, and the bottom part is the safety critic that we do, which I'll explain. Okay, I'm not sure which file it's in. I have that stored somewhere else, but I can show you maybe like a sample. The code is really clear on how you like add nodes to the graph and how you add edges into the graph. So that'll probably clarify your first question. But yeah, I'll look at that at the end. Okay. So here we had GRPO's advantage function, and here we have DGPPO's version. And so I think someone asked the question last time, like, how do we switch, right? Like, how do you actually enforce the fact that you're not going to abide by your safety constraint? And that comes in with like some sort of binary decision variable, which is saying, maybe we'll like break down what this equation is saying, but the first part will be executed if you were within a safe state. So that's what this part means. That means that your barrier violation is less than 0, so you're not violating the barrier. If it's positive, then you're violating the barrier. So then this is activated. Right. So the first part of this part activates when you're in the safe set, and AGAE is just the calculated task advantage. So that would be whatever reward, normal form of the advantage that we get from the reward critic, which is the top part. And then if we now violate it, this becomes 0, and we only have this negative part, right? So we're saying by taking this action, you will violate your safety constraint, and therefore you'll have a negative advantage, which then would lead to, lower, which would impact the loss accordingly, right? That's basically the equivalent of a negative reward.
So the agent prioritizes to enter back into the safe region.
Yes, as opposed to doing optimal action. Right. And the other differentiation you get from this is like, maybe I'm like veering towards the wall, right? But I haven't crashed with or like the next step I take is not going to make me crash into the wall. So if for some reason that's a more optimal action at the time, it'll let you continue to do that. Like it's not gonna force you to stay in the midline at all times, right? As long as you are within the safe set, it'll let you continue to take whatever action you want to take. So, which is why either you use this part or you use this part. You're never like trying to balance both safety and like optimize your reward. And so this is just some like negative weight, to basically put you back into the, safe set. Yeah, so this is the core concept, right? You mask the task rewards if you will have a breach in your safety barrier. And now when we think about how the loss gets calculated, we talked about how like PPO uses this clipped loss. So this is the format of the clipped loss, which basically restricts how far you can move. But the important thing to keep in mind is like none of this really changes. The only thing that changes is how we define this advantage, which is defined by that formula. That setup makes sense? Like how we switch between the two and why we're like sticking with the PPO structure and how that makes sense.
If we are getting into this safety problem, which means we're out of the safe region.
Yeah.
Change the advantage of my event, right?
What do you mean?
I don't understand how it makes sure that I'm not going to make that action. This is loss, right?
So this is loss,
Yeah.
but it would be the equivalent of getting like a negative reward. So in this case, like they're using the advantage as a proxy for reward. And basically by your erase, so the first component would be the reward as calculated by your reward function. The second is your.
Yeah, that. So
yeah.
if I go to negative reward, does it affect my immediate step now? That's what I want to.
Like your next step? It may not affect your next step, but it would, no, I think it does, it should, yeah.
Right.
It should push you back into the safe state then. So like, you may still, in your next action, you may still, no, yeah. So this decision is essentially made right at the border, so it would be essentially pushing you back into the direction you came, like pushing you back towards the center of your safe step.
That I don't understand here, but I'm not sure which point. So this is
okay.
the loss, and this is what I'm trying to optimize. But then my action is determined by actor, right? And how does this even enforce the actor to not output an action that would give me a negative reward?
So what it would enforce, it would tell the actor to ignore the action, the like proposed action from the first step. Like basically, if I was told I should go forward, but going forward would like I would crash into the wall. This is meant to say ignore that part of it. So
yeah, but this is like in a way because it's a loss, right? It will send a gradient to my actor function that will kind of downgrade this opportunity to go into non-safe region or hitting the wall, right? So, but it doesn't guarantee. That's what I'm like.
It guarantees that you don't take into consideration your goal. That's what it guarantees, but no, it's not a hard constraint mathematically speaking.
Yeah, so for example, if like before this, imagine my actor would like the softmax over actions, like let's assume it's a discrete whatever, and there is one action move forward, which is hitting the wall.
Yeah.
And I have very high probability for that before all of this. So now this will say that update your actor weights in a way that this action gets lower probability. But it doesn't guarantee that after this gradient update, it will not be the maximum, right? It will.
Yeah, but there is an indicator functioning. It becomes a negative probability. So in any optimization, you would never choose it. It doesn't just add to the prior probability. It just erases the prior and describes a negative one.
But it erases here in the loss, not in the actor's output.
The actor that maximizes in that given loss function. So for the actor now, that direction is negative reward. So it wouldn't pop up as an optimal in any optimization algorithm, right?
But it's, you do just one gradient step right here. This one step would not be enough to
It's shifted.
see what I mean.
So
We
you
are
always-
guaranteed that we do this step with respect to the understanding that we are going to optimize our safety.
You step in the optimal direction. And this guarantees that that direction is never optimal. If your algorithm allows to go in non-optimal
Yes.
direction, then you're unsafe. So
Yes,
this
yes,
works
yes. I
only
think-
if the algorithm always goes in the optimal direction.
Like,
What if
sounds-
you
that
go
sounds right.
in one step, you get into the unsafe territory, you incur this -B penalty, but then you have much higher advantage.
Yeah, this algorithm doesn't allow you to do that because, as she explained, so
Have a
your
negative-
drone explodes and then. there is no
Negative
further-
reward for one step, but then maybe much better reward.
Yeah, but this is not that, so this is just for one step, so just one step beyond the calamity, you just prevent it by artificially erasing the old, you see the indicator functions in the black box in the first line. So basically, you erase the old reward function and you prescribe a negative reward function at that point, this discontinuity.
yes,
So it never allows you to do one step further.
you know, I think the implementation question is, when you have this loss. And before you make your next action, how far do you optimize with this loss? Like in regular LLM training, you do just one gradient step, which might not be enough to reach the optimum of here. So that will,
I mean, you just tune into this constant, like, it seems like to me that the question is just how big is this constant?
Yeah, like V, right?
I think still,
Yeah.
Yeah.
if
Still
you
with
do
one
just,
step, you cannot guarantee that you will not hit the wall. I mean, if you
Yeah.
encounter the same problem like 100 times or whatever time, and then you actually understand that, okay, like taking the action go forward when there is a wall in your ahead of yours, then that's it the reason that I'm getting this high reward, high negative return. Right, so I mean, after one phase, you cannot guarantee that that's exactly what was the reason that I got this negative reward. But after many times,
there's no confidence rate to guarantee.
Yes, basically, you're just allowed to get there, but you may return to the same point many times because you didn't get why,
yeah.
right? You got there.
You just know not to
forward
go
because
forward,
it
yeah.
very sharply gave you a negative reward. You step back, but you may come back because you step back to the previous position and the previous landscape forces you forward again. So maybe a trap in a sense.
So this is, yeah, so I think this manifests in, if you remember any of the examples of during execution, after training, after learning the safety barriers, it just, you'll see that even during execution, it might go like this, it might walk around. It hasn't learned that the straight path is this safe path or the safest path where you don't have corrections. It's just learned that, so when we say it learns the safety barrier, the barrier function, that's what it's learning. It's learning that like when I am, like if for some reason, like these 5 tiles are the ones where I'm unsafe, like when I get here, if I realize that crossing over here is going to put me into the negatives, then all I learn or all I know is that, again, when I get here, like this is a problematic step, so let me go back into where it's safe to go, or like where it's positive.
I think I believe that for proper safety implementation, we should have another constraint on the actor. Not only through the loss, but some hard constraint on the actor itself. So if there is an action that creates a negative reward, this information should be available not only through this expectations, gradient, whatever, but also when when the actor predicts the next step, it should, I don't know, some if statement there that if this particular action triggered a negative reward, then just
like don't do it, yeah.
It's not necessarily always the case, right? Imagine when you have like, I don't know, 2 possible actions, and one of them you knew a priori that you need to put this hard constraint, not taking it ever. But who knows, maybe you are in such a critical situation that the other action that you allow to do will take you to even worse conditions. So by exploring it, kind of we hope that it will learn the thing. But I agree that some hard constraints or some contextualization or conditioning of your policy can be beneficial for at least faster learning, not exploring of these bad edge cases.
I think what the
That's a
most
good point.
confusing thing for me is that this DGPPO is sold as a kind of guaranteed safety. But it's not really. It's guaranteed safety if you optimize this or reach the optimal state of this loss. But I don't think you do that always, right? Or maybe you do it and then
Like, is there ever a guarantee that we can give with RL? I mean,
yes, I mean that's why this DGPPO and we should look how strong they sell it in the paper.
So I think like the point is it enforces safety a lot better than other approaches. And like by like their whole shtick is basically decoupling the learning of what actions you take and decoupling the safety part of it, right? So like mathematically CBFs guarantee safety, but yes, maybe through the learning, like maybe through this learning process, there is like situations where it's not like guaranteed, like whatever you're like getting at. But like for most use cases, like for our use case, this is sufficient of a guarantee.
infinitely long training, I can see that one can guarantee, right?
Sure, yeah.
Finance, like, you know, your loss function never reaches like the optimal point. One can prove, I think, from this loss function, the optimal policy is that you never hit the wall.
Yes.
Right? You can guarantee that, but it does not mean that after final time of optimization, you can guarantee the state.
It's probably the distinction of mathematical guarantees versus like practically what actually happens, right? Like what we can train.
One can compare like the convergence rates and stuff, or like this, you know, critical failure rate in one optimization pipeline and the other optimization pipeline. See, maybe in this case it's exponential, the other case it's not.
Yeah. Okay. Does everyone understand the advantage function and like what it's getting at, or like what it's trying to do, or like why we're separating, why we have these indicator functions and how that influences like whether we activate our like safety mode or whether we just continue with operation? That makes sense to everyone?
You said that author predicts the policy.
For the actor is big.
Action of the distribution,
Mhm.
the critique, the value, and also whether it's an unsafe state.
Yeah, so there are two critics. So there's like, that's why we have this. There's critic one, which is just the normal critic that we deal with, which is assessing the actions and the policy. And then there's the safety critic, which is still assessing the action taken, but it's only doing that step of like, if I take this action, am I unsafe or safe? And then the values, this VL and this VH, the values we get from there are basically what influence the VL would be the AGAE, that part.
The part influenced by the first
First
critique and
part,
the right.
exactly.
Oh, okay.
That's kind of it. So the CIM, this thing, is what would come from the second,
If
from
the
the
second
second.
critique's value is larger than the threshold. the
Yes,
second-
which is positive. So we say if it's positive, if that value is positive, then it's a barrier violation.
Okay.
And then then that influences the indicator function that's activated. And this is like the magnitude, right? The magnitude of how bad of an action or like how much of a violation it is. So, like if it's more of a violation, then you want to take more of a corrective action. That's where that falls into place.
The second critique is just binary classification.
It's binary in that it's either safe or unsafe. But like, well, actually it's not binary, right? Like this value is technically continuous because this is the magnitude of how safe or unsafe you are. But it only matters, like that value only matters for the unsafe part. Like, so we only care about how unsafe you are, and you care, like if you're safe, that's fine. Doesn't matter like how close to the unsafe border you are in the safety, that doesn't matter. As long as you're like below that 0 threshold, which represents the border, then you're.
And I know how the policy, you can update the policy, I know how you can calculate the value for a state,
Mhm.
rewards, but how do you update this now? And ask about the critic predicts as how unsafe it is in this specific state.
So it's all,
Discount.
yeah, I think it's all learned this, sorry, say that again?
Discount with the negative reward from unsafe states. Person.
Like you're saying, if you were to take this unsafe, I don't know that I understand the question.
What is the laws that trains this?
Oh, okay. So maybe this is the full visual. Okay, so for the safety part, which is this part, you yeah, here. We so the well let me see how I answer this question directly. Okay, so we get our policy, we have the critic part act on the agent state with noise. So that's taking the policy, that's what the pi with the X is representing. And then for the second part, we're taking the mean of our distribution, which is saying like on like everything above this is above average behavior. And what we want to do on this part is like, I don't know if this is a useful visual, but it's basically trying to show that within, so for agent 0, which is you, given within your sensing radius, like what are the regions that are safe for you to like reach and what are not safe to reach, and that's they just use a mean squared error between. So I think like the encoding along the edges is information that is used to inform this graphing.
Okay.
Yeah.
Thank you.
And then the output of this is what we saw on the other slide, which is basically what is actually like how bad of a decision is it, like how much of a safety violation is it, and like is it safe or unsafe. So these pieces of information come in. From here we get our advantage, which is calculated up here with our stochastic rollout, and then this gradient propagation, the gradient projection is essentially what we are representing in that advantage function. So that function plots itself in here. It takes inputs from these two branches, and then it outputs the PPO loss as we saw here.
Mm-hmm.
And then that gets used to update the policy. And then it just reads. Okay, and then this is kind of the last slide in here, but this is kind of what came up in discussion today and in the past. But like I was just thinking about like can the GRPO technique, the style of like spawning multiple examples and seeing how you compare to that, can that be used for defining safety? If so, how do you have to like how do you define a safety baseline on that? And like I don't have a sense of that. But like there's a world in which maybe removing the critic part of the network is useful. Like we talked about how it's memory saving. If you have a cheap way of modeling trajectories, then this is possibly a feasible approach. But still, there is an open question of what would it then mean to be safer, right? Like if you have an average sense of the trajectories, that's not a guarantee on safety, but maybe there's a way to redefine your guarantee on safety with looking at various trajectories that could be spawned from that one policy. And the second part came up in a discussion with the VLM team today, but I think the motivation of that question was like, they're trying to integrate RL into their system, possibly with GRPO. And then the question was like, is there a way, like, one, is there a value in imposing hard constraints? Like, what would these hard constraints impose? It could be safety again, it could be something else. And if we do so, how would we do so? Right? Like, how would you actually impose this CBF concept into a GRPO structure? So they're like questions that I don't have answers to. It's open to the group in case you have ideas, especially from people who proposed the idea. So Harat, if you had thoughts on either of these, since you asked the question,
Can you go back to the critique definition? Where was that? Right. Critic is
This one?
essentially the critic wants to learn the expected reward, right? In a way. Critic is learning the value function, and value function is the future reward expectation.
So the critic is also
Sure,
a network, yes?
Yes,
Okay.
the critic is a network.
So what GRPO is saying is that you don't need to model that, you just put rewards on the current actions.
Yes, and you see how it compares to them.
Yeah, and if you have a distribution of possible current movements, let's just understand which ones are good, which ones are bad, which is only based on the reward for the current step. It doesn't have this future expectation, right? It's
Correct.
only at this step. And GRPO says that if you do it on like the distribution level, not on a singular, but like 16 rollouts, if you figure out that the rewards for these 8 ones are better than the other 8 ones, let's just maximize the actions towards those actions which bring those relatively good rewards. And in that case, you won't need critique much.
Yeah.
So at least the task critique part can be replaced with that, I think. So if you if there is no safety critique, if it's on task critique, I think GRPO says that I don't need this.
Correct.
Let's do this other trick and get the same result. So now the question is mostly about what do you do here? Like if you did this same advantage calculation for GRPO rollouts, you could still do that, right? You could still say that this action is hitting the unsafe territory, so its reward is very bad, and it will never get the
So in your example, you're saying you pass in your patches, you pass in the map, and you say it predicts forward, right? Let's say, and you're saying forward is an unsafe action or undesirable action for whatever reason, if you have some notion of unsafe or undesirable. And then you can activate it in the same way, right? Activate this constraint and see. Yeah, that makes sense. I think like
you could still like the next slide when you have this formula. This is like an advantage formula which still exists in GRPO. So
you just put your GRPO into, I think, GAE. Like you can just
exactly.
You just plug GRPO into GAE. The only question is I don't remember exactly implementation wise how we do this scaling to a negative thing. I just missed that part. So I think that requires like some tasks.
Is it like this scaling?
Yeah, the scaling on how
like how do you know how bad it is?
Yeah, so that is because that goes outside of the like that group, like information outside of that group concept for that part. But you know just
like
negative.
Like how we define,
like imagine I blindly take this advantage and put into GRPO.
Yeah.
What would happen? It calculates those numbers, and some of them would be okay. So in GRPO there is this normalization step, right? Which when you give rewards for all actions, like imagine I have 16 rollouts, I have 16 rewards, and I take the average and normalize with that average. So if I just had, I don't know, imagine 15 out of 16 rollouts go into unsafe territory.
Mhm.
Mhm.
Very bad case. The average would be somewhere in these unsafe actions.
Mhm.
So in pure GRPO, some of them would get positive rewards. Right? Because there would be,
Like some are technically above average in some metric. Is
yeah,
that what you're saying?
Yeah.
and probably that's where you have to be careful. You don't want any unsafe action to get any positive reward.
Well, you're putting it into the sample level, so you're saying,
Yes.
let's mask out all of the unsafe rollouts in the group, for example.
Yeah,
Right, exactly,
Yeah.
minus infinity.
Yeah, something
Then
like that.
it's
So
also-
to make sure that the way you normalize in GRPO,
Hmm.
you ensure that all unsafe actions stay negative.
Correct.
And
Yeah,
then
so
if
you're
you
only
have
taking the
this
consensus of your
one
safe ones.
safe action, you can continue GRPO style training.
Sure.
I don't know if you have any guarantees in theory that if you train with GRPO this way, you will. I think part of the things that guarantee this DGPPO is that probably there is a proof somewhere
Yeah.
that if you train enough with this loss, you will satisfy this constraint for all actions. I'm not sure this type of proofs exist.
I think they have some version of it in the appendix, like
Yeah,
in that direction. I don't know if it's
Yeah.
Not
We
completely
can
sure,
look
but
into
yeah.
that, but I think technically, I see that this safety part can be put into the RPO with this caveat that we should be careful that it never gets positive reward for any unsafe action. Yeah, maybe there are extreme cases when all rollouts are unsafe.
Yeah.
What do you
What do you
do
do then?
there? I don't know, you don't update, you but it's a trap, right? It's that,
Yeah,
I don't know, you generate rollouts as many times as I don't,
like until you get something.
yeah,
at least one level.
maybe this type of crazy corner cases can happen. But other than that, probably this definition can be transferred to GRPO as well
Mhm.
without any critique.
I think so. The useful thing about the CBF framework is that, like, we are talking about safe and unsafe sets, but anything that you want to, any way that you want to split the space up into like two different, sets, whether it's safety or whether it's, I can't really think of anything off the top of my head, but like, the point is if there is something else you wanted to model where there's this binary of like, this is the thing you want to do and this is the thing you don't want to do. As long as you have a way of representing and learning that, like, if you model it as the CBF, then, all you're doing is you're changing the states and the values that are relevant to the calculation for what determines safety. Yeah.
Actually, one question. So imagine like with our training or not training, but our like simulation is a quite long process. Let's say it simulates 2 hours of, I don't know, drone flying around.
Sure.
And maybe perform quite well during this, 1.5 hours
Mhm.
of the entire time. But then the last half an hour, something bad happened and maybe it went and crashed. So I was wondering, like, if I understood correctly, with this like loss function, we kind of ignored the entirety of the simulation and only negatively reward the guy if it crashed at the end of the day, right? Is it optimal to disregard the entire process and only, focus on this final negative thing that happened? I don't know. Maybe it's possible to like break it into 2 parts and like use the useful part of the simulation and learn like maybe if you're not far from the wall, but how you perform and how you optimize the entire policy, and then like, okay, maybe the final part when it crashes, then this is a separate problem. I don't know.
Like you're saying, during, so. Okay, so, this is a on policy process. So it's like, it is basically learning, what is it learning? It's learning, like, what is it? the first part of my trajectory is great. I make a bad step next,
Yeah.
what is like the next best thing to do, right? So I don't know that, or maybe I'm not understanding your question correctly, but it's not throwing it.
So it's question about like what you try to optimize, right? If it's like, every time you play the same game with everything is the same and you try to optimize block after block in a way, then maybe I can understand this. But if you are trying to optimize the entire policy of like, what action you need to take, given the state and I don't know, whatever, right? Then, you had a lot of like, and if, of course, if also your policy, if your process is stochastic, then every other simulation is different, right?
Yeah.
And you like learn a lot from the environment because of this stochasticity. So you get a lot of useful information. Maybe the final step was a bad one, then okay, we want to know that it was bad, but we want also to have some positive signal for training the entire policy from the good part of our simulation. So if it just makes that step, it's stuck in the loop because it's made so that it goes back and the game goes to the outside territory. So if we have some time limits for the working, we can say that the negative value that the agent gets because of the bad action is proportionate to the time left to operate. So the agents that make this bad decision late get some reward, and because of that, agents continuously learn to make mistakes later. No, yeah, sure. That I agree, but it's like when you say you kind of don't mean that we need to erase the entirety of the question, why do we erase the entirety of whatever we saw before the crash? You know what I mean?
We're not erasing.
From this, when I see like it's an indicator function, right? Whatever I did and it was good, maybe I earned some rewards and I say, okay, forget that. I don't want to have any positivity if I crashed at the end of the day. And I delete it with this indicator function, and then I give you minus mu whatever if I crash,
This is so I don't think it's like erasing the history. I think it's just saying that like this next step would take me into unsafe
It's
territory.
indicated by I, like there's the index.
Yeah,
so I think
exactly.
It's just.
It's for your time step.
I think, I see, so
Yeah.
I think, yeah.
So you optimize by like what you added, right? So you were already in this state and you take like, I don't know, your 16 actions or whatever, take the next action and see what happened. And like, okay, if it was a bad action, okay, then it makes sense. Okay, so I thought
yeah.
it's like, the constraint in all the entire simulation process, or the entire policy. Okay, then
The rewards are discounted, right? So the actions closer to the start will be penalized more than the actions before that.
So I guess like assuming you did crash, yeah. But like pointing out the I here is important, and that like this is only for the single time step that you're looking at right now, like your current time step. The next action, you're ignoring the reward that you could get out of that action, and then you're saying like this is bad because it steps me into the wrong direction. So the erasure is only for that one. You're temporarily forgetting like what, like if you took that action, what reward you would get out of that, and like what state that would put you in.
I think the only bit of information that we lose here is that if there were two actions that were both unsafe,
Sure.
and one of them was closer to the goal than the other.
Yeah.
This will treat them equally. Right?
Yeah,
Don't
yeah.
know that this is
That's correct.
still unsafe but better. That part is kind of missing, but from okay.
I think like this is the whole thing of like you can't be both safe and optimal all the time. Like there's no guarantees on safety and optimality. It's just guarantees on safety, and then you try to be as optimal as you can. Yeah. Cool. Yeah. Any questions?
I think this gives an idea on how we could add safety in GRPO. We can try to, instead of putting it in the reward, like colliding with the building is negative reward, we could add it in the advantage calculation step. So like no matter what the reward is, we adjust the advantage of this particular rollout to negative. Like you could do GRPO without the safety part, you would get the advantages, you would normalize them, blah, blah, blah. And then if it also collided, you do
Mask
this
it out.
trick and make the advantage, like hard code the advantage to be negative. And this way you ensure that unsafe options never get positive reward. Interesting.
Like, I guess in the GRPO example, it's not just, it's like throwing it out, right? Like, if it violates, then you throw it out. You don't map
Yeah,
it.
you could
Yeah.
even, yeah.
And then you only like deal with the ones which are good. But yeah, I mean, we talked about edge cases where like what do you do when you have?
Maybe throwing it out is not good because it doesn't give you signal. So I think in GRPO, even your negative examples kind of give some signal, right?
Probably, yeah.
So you learn to not do that.
You said that max negative reward on all of those unsafe ones. It
Yes,
depends if are you plugging the GRPO into the AGAE here, or are you putting vivid equation into every GRPO advanced calculation?
I think.
Those are, I don't want to, which one you're trying to do.
The second one?
I think I would add this after GRPO, so if GRPO advantages are calculated.
In there, you put it in there, in the AGAE.
In the first
Yeah,
part.
it's mentioned, yeah. That would be interesting.
I was also, yeah, thinking about like possible applications of the safety thing.
Mhm.
So, I'm not sure, like in case of molecular optimization tasks, do we miss this, or is there something that can be defined as the safety task?
In our case, it would be like, for example, in the scenarios that we're playing with, we have, so to give you some context, when you prompt the language model to generate a new molecule, again, you can do RL style rollouts, like GRPO rollouts, so it gives you many candidates, and then you can score them somehow.
Okay.
And then some of these scores might be so critical that you don't want to even go there. For example, I don't know, it's a matter of class definition, right? You could say that if it's not drug-like, so drug-likeness is a critical safety component for us, and be very hard about that. And for all others, we just let them to be optimized as much as possible. So you could take some of our, so we do multi-parameter optimization anyway, so our reward consists of 4 terms. 5, 6, whatever. So at some point you could say that, these 2 terms are critical. Let's put them in this fashion so that it never even thinks about generating them.
Yeah.
So
Speed up the process.
Yeah, and then the model focuses on the other.
Yeah.
That's also.
I mean, I don't know if there's like a notion of like stability or things like that, which if you were able to define that as a stable is a safe set, like molecular, I don't know enough about biochem to like know how well that can be mapped out and stuff like that. But
it's a matter of like, do you want to go through this unsafe territory, even if it leads you to a better place? Like if you are a robot, you don't want to fall off a bridge, even if after that you might be able to climb to a better place, right? Maybe in molecules, it's not that important, so you could go into an area which is not stable, but then you
come back out,
come out of it in a different direction, which is both stable and good, right? So maybe this is not very important for us.
Yeah, that's true. Cool. Any other comments, questions?
One of the very first pages, you had the definition of this value function or what, yeah, this one, the very last, is the display formula.
Mhm.
So this is basically a equation for the unknown function B.
Sorry, say that again, sorry.
This is the system of equations for the unknown function B. On with the domain of actions and taking basically real numbers say. So do we know if this equation has any solutions or whether the solutions are unique? I mean, this is a matter of defining the value function, right?
I don't, yeah, I don't know the answer to that question. It's a good question. Do you have any intuition?
Yeah,
Or do you know?
depending on R, you could.
Exactly.
Yeah.
The R's and the conditional probabilities are the coefficients of your equation. Depending on them, it may or may not have a solution, or it may have many solutions, and then you have a question which one to choose. Okay?
Yeah, I think the assumption is that there is some solution that we're trying to approximate.
And maybe it's okay if there are multiple.
Yeah, but then maybe in the process of approximation, you're jumping from one solution to the other without even realizing it.
So yeah, could be. But I don't think it has negative effects on anything other than maybe slow convergence or.
I don't know. I mean, if this V has any real world, say, interpretation, then it might be important. Say in physics, you have this century-old problem of choosing the right boundary conditions for your PDE. So, and then you have to implement possible solutions, and every boundary condition is about a very precise physical situation. It's important to choose the right conditions. So here I can tell, but it may make sense.
I mean, technically, the solution also depends on gamma, which is chosen in the way you ran.
Right, but these are all parameters. These are the coefficients of your equation, and depending on them, you either have a solution or you don't, or you have many, right? And it's not a differential equation. It's a kind of functional equation which shouldn't be too hard, or maybe too hard. But I guess the question worked that in.
If I remember correctly, for some types of Markov processes, Markov reward processes, you can always find the optimal. It sounds pretty maximization algorithm.
Yeah, the point is, one thing is try to optimize it up to a certain level. So, say numerically, you are always
find the best one.
numerically you're always within an epsilon accuracy, but conceptually, you maybe want to understand what you are doing through. So, what you are chasing, does it exist at all, or is it just
To define the start state, the transition to the states, this value for the start state, you can maximize the
It's not
value.
the chain, it's cyclic loop. So for every S, every other S enters the equation on the right hand side through the expectation of S prime. So it's really interconnected backwards loop equation. You can't solve it iteratively. So essentially that VS prime stands for the expectation over all possible next steps with respect to that conditional transition in the black box, the third line, right? PS prime given S and A, right? Times VSA times gamma. So all possible S prime figure out on the right hand side for every S. So you can't really decouple these equations and make them a chain to solve step by step. So it's at least from first glance, it's a trivial question. maybe it's not difficult to solve, but not technical and trivial question.
Yeah, I mean, it's a good point about that, like, if you have multiple solutions and like, how do you know that you're not switching between solutions? Like, that's a really good point. But I like. I imagine that you're,
This is
yes.
a question you often get engaged with.
Yeah, exactly.
This is more of a theoretical question.
Yeah, and I think typically like, so sometimes you'll like develop a model and it won't learn what you're expecting it to do. It won't converge. And like we can maybe, sometimes you're able to pick out the reason for why that is, and sometimes maybe it's more about like model level change. And so it would be interesting to see if like what you're saying, if it's a matter of switching, if it's like hopping between solutions and not converging, or if it's like something else in the, like it's just completely unsolvable.
But as you know, 90% of time, what practitioners do works. And
Yeah.
the theory is to explain the rest.
Sure, yeah. Yeah, I mean, that's a very good, like thought-provoking question, which I don't have the answer to. Yeah. Cool. I think that's it for today. I haven't yet decided what I'm talking about next week with RL extensions. So if anyone has any desires or recommendations, just let me know. Cool.
Also,